In this video, we'll be doing an example of problem solving utilizing the ideas of pressure and force. The problem statement is as follows. An aquarium has a saltwater fish tank that is 22 meters deep. There is a window at the bottom of the tank for visitors to look through. First, we are asked, what is the pressure due to the water at the bottom of the tank? Then, what is the total pressure the window feels? And then finally, if the window is 2.8 meters wide and 1.9 meters high, what is the force felt by the window? All right, so as always, we begin the problem by thinking about what the problem is telling us. And there are two pieces of information here in the problem statement. First, we are told that the aquarium is full of salt water. All right, and we're told that the tank is 22 meters deep. So, writing out that data, right, we are told that the tank has salt water in it, and so therefore the density of salt water is 1,025 kilograms per cubic meter, and the depth, which remember we designate with the letter H, is 22 meters. Right, the second step in the process is to figure out what the problem is asking us. So we look at the problem, and it's a very straightforward request. We are first asked, what is the pressure due to the water at the bottom of the tank? So we're being asked for the pressure exerted by the salt water in the tank. Step 3 is then to find an equation that relates what you are told to what you are supposed to find out. In this case, the equation is for the pressure in a fluid, the density of the fluid, in this case salt water, times G times the depth. Once we have found this equation, it is a straightforward task here to plug in the numbers. The density of seawater times G, which we will take as 9.80, and then the depth, which is 22 meters. This allows us to calculate the total pressure exerted by the fluid, which is going to be 220,990 newtons. Since this problem has two significant figures in its data, the 22 meters for the depth, we would report this as 220,000 newtons for the pressure due to the water at the bottom of the tank. The second question asks us, what is the total pressure the window feels? This is different from the answer to the previous problem. Previously, we calculated the pressure exerted only by the seawater in the tank. However, we must recall that there is air above the tank. This is not an aquarium on the moon. So there is air above the tank, and so the total pressure felt by that window is going to be the pressure of the seawater plus the atmospheric pressure above the tank. So that is 220,990 newtons from the water, and then another 101,000 newtons per square meter. Newtons per square meter from the air above the tank. This then leads us to a total pressure of 321,990 newtons per square meter, or if you prefer, 320,000 pascals, because that is the special unit for pressure. So we would report a total pressure above the tank of 320,000 pascals. The third question asks, if the window is 2.8 meters wide and 1.9 meters high, what is the force felt by the window? Well, this is some new information, and so we have to write that down. We are told that the height of the window is 1.9 meters, and the width of the window is 2.8 meters. This allows us to calculate the area of the window, which is 1.9 meters times 2.8 meters. And so the window has an area of 5.32 square meters. These data are important because we have the formula for pressure. Pressure is force divided by area. So doing a little algebra here, we come up with a formula for force. Force is pressure times area. And so we take the total pressure felt by the window, 321,990 newtons per square meter, and we multiply by the area of the window, 5.32 square meters, and that leads us to a total force felt by the window of 1,713,000 newtons. To two significant figures, we would report this as a force of 1,700,000 newtons felt by the window. Now, must remember, this is the force felt on one side of the window, the side of the window that's actually in the water tank. We wanted to figure out the net force felt by that window. In other words, to assess the possibility of the window breaking, we would have to figure out the force felt from the air pressure on the other side of the window in the observation room. We would then subtract those two forces to find out the net force felt by the window. But we are only asked for the force felt by that window on the side with the water tank, and that is 1,713,000 newtons, or to two significant figures, 1,700,000 newtons.